Okay, so in this video we're talking about areas under the normal curve. So again, the normal curve, we know the mean is always in the middle, and the standard deviation kind of tells us the distance from the mean to inflection point. But other than that, unless we're talking about the 68, 95, 99.7% rule, we don't know how to calculate probabilities of experiments exactly until now. We're going to use calculator. The first way is called the normal PDF function in your calculator, and it stands for the probability distribution function. That's what PDF stands for. And it's used when we're looking for exact values. In your calculator, what you're going to do is hit second, vars, and then go to the distribution menu. Let's do that together real quick. So second, vars, go to the distribution menu, and then it's the very first thing, normal PDF. Once you get there, you're going to need to know three things. The exact value you're looking for, the average value, which we use the symbol X with a bar over it, and then your standard deviation, which is still the Greek letter sigma. The other calculator function that we're going to introduce is the normal CDF function, which stands for the cumulative distribution function. And we use it to find under the areas under normal curve between two values. So PDF is for exactly one value. The CDF is for between two values. That's how you tell them apart. And again, in your calculator, all you do to get there, second vars, you get to this menu, and then it's the very second option, normal CDF. For normal CDF, you're going to have to know four things. You're going to have to know your lower bound, your upper bound, your average value, which again, we call the average value, just X with a bar over it, and then your standard deviation, which is still the Greek letter sigma. Okay, so now let's actually try this with a few examples. In this example, we're told that adults' women's heights are normally distributed with a mean of 63.5 inches and a standard deviation of 2.5 inches. Approximately what percent of women have heights between 61 and 66 inches? Well, the key word here is between. 61 is our lower bound, 66 is our upper bound. We were given the mean, 63.5, and standard deviation of 2.5. Well, since our keyword is between, that means we're going to use the normal CDF function. So in the calculator, I'm going to pull up the normal CDF function. If it helps you to draw it out first like this, we have lower bound with 61, comma, upper bound 66, comma, average value 63.5, comma, standard deviation 2.5. If we type that in the calculator, we're going to get a number. So let's type that in. So 61, comma, 66, comma, 63.5, comma, 2.5. That's the normal CDF. And I get 0.683. So 0.683. Which in other words, that translates to about 68.3%. So here we get a problem, 68.3% of all women everywhere fall within 61 to 66 inches tall. 68% of all women. Okay. We want to give a range in which approximately 99.7% of all women's height should lie. Well, that could be difficult, but that 99.7% sticks out to me. That's part of our 68, 95, 99.7 rule. So 99.7 was within 3 standard deviations of the mean. Of the mean, X bar, or mu, whichever symbol you want to use. So here, and I want to use mu, I like mu better. I just do. If you like X bar better, you use X bar, but they essentially mean the average. So within 3 values, so my lower bound, we're looking for a range, so that means we need a lower bound and upper bound. So LB for lower bound, UB for upper bound. So the LB, our lower bound, is going to be the mean minus 3 sigma, our upper bound is going to be the mean plus 3 sigma. We just plug in what we know now. The mean height for women was 63.5 minus 3 times our standard deviation of 2.5. That was our lower bound. Do the same similar idea here, 63.5 for the mean plus 3 times our standard deviation of 2.5 to calculate our upper bound. Use the calculator to help us out. No big deal. So 63.5 minus 3 times 2.5. That's 56. So my lower bound is 56. My upper bound, 63.5 plus 3 times 2.5, 71. So what this means is that 99.7% of all women everywhere, their heights are going to fall somewhere between 56 inches tall and 71 inches tall. So if you're a betting man, if you say, you go up to some random woman on the street and you're like, hey, I bet you're somewhere between 56 inches tall and 71 inches tall, you're almost guaranteed to be correct because 99.7% of women, based on this data, are supposed to fall within this range. Let's do another example. Here, we're doing a probability experiment that is pretty much, we're flipping a coin 10,000 times. We want to know the probability of getting exactly 5,689 heads. Before we do that, what we need to do is to calculate our mean and our standard deviation. So in a normal coin flip, we're talking about heads. So let's call 1 equals heads, 0 equals tails. That's for 1 coin. So to figure out our mean, so for 1 coin, we're going to go to the calculator. So hit Stat, Edit, and I'm going to put my one and only coin in L1. So 1 for heads, 0 for tails. Hit Stat again, go to Calc, and you're going to select the very first option, 1 variable statistics. Well, we'll look at all the symbols and information that it gives you. It tells you that the mean, X bar, is 0.5. You have a 50% chance of getting heads or tails. That kind of makes sense for 1 coin. And our lowercase sigma is 0.5. Okay? Well, what you should know from previous class is that there's something called the variance that you can calculate directly from the standard deviation. The variance is just another measure of spread, but all it is, the variance is just sigma squared. So what we can do to find the variance is take that 0.5 and square it. So we get 0.25. So the variance is 0.25. Now you might be wondering, why do I even care about the variance? We haven't talked about the variance at all in this unit. Well, the variance is something you should have learned in a previous class, so I'm assuming that you know it. We're going to use that to help us out. Again, everything here in red was just for 1 coin. We need 10,000 coins. So what you should have learned in a previous class is that the mean and the variance are multiplicative. So that means once you know the mean and the variance for 1 coin, all you have to do to find the mean and variance for 10,000 coins is multiply by the number of flips. So for 10,000 coins, the mean is going to be our 1 coin times 10,000. Well, that's pretty easy to calculate. 0.5 times 10,000. If you can't do it in your head, use calculator. Just show you that. So 5,000 heads. That kind of makes sense. If it's a fair coin, which we were told it's a fair coin, we expect on average, if we're flipping a coin 10,000 times, we expect on average it should show up about 5,000 times. Okay, the variance is also multiplicative, so same idea. The variance that we got for 1 coin, so 0.25 times the number of flips we're doing, in this case 10,000. Well, that's going to be equal to 0.25 times 10,000, which is 2,500. Now, the last thing that you should remember is that the standard deviation is not multiplicative. So you can't take 0.5 times 10,000 and get your standard deviation. That's why we needed the variance. Because once we had the variance for 10,000 points, we can work backwards and get the new standard deviation that we need. So we want to go from sigma squared to regular sigma. So I need to take square root on both sides. So my standard deviation is going to be equal to the square root of the variance, which was 2,500 in this particular case. So the square root of 2,500 is my standard deviation for 10,000 points. All right, great. So we want to know the probability of getting exactly 5,689 heads. Before we do anything, regardless if we're doing normal PDF and normal CDF, we had to know for 10,000 points what the average value was and what the standard deviation was. The calculator requires that information. That's why we had to do this scratch work beforehand. So since it says exactly, this is a normal PDF. Excuse me. And normal PDF, what it means is your exact value comes first at 5,689, comma, your average value for 10,000 points, that was 5,000, comma, your standard deviation for 10,000 points. Standard deviation was 50. We're going to type that in our calculator, or we're going to get some information. So I'm going to hit second bars, option 1 for normal PDF. Again, type it in exactly the way we wrote it out as our map, comma 50. And it's a really, really small number. Make sure I type this in correctly, 5,689. Okay? So the probability is an incredibly small number, 5,689, 5,000. Let's go back and make sure I've got everything in the correct order. X bar, standard deviation. Okay? So what that means is I essentially have, according to this, doesn't make a lot of sense to me, but I'm going to trust the calculator. It says that I have pretty much a very small, almost zero chance of this happening. That's okay. I mean, it might be true, there's a zero chance of this happening. What's the probability of getting between 4,900 and 5,100 heads? Okay, well, between, that's keyword. So between means normal CDF. Again, it's your lower bound, so 4,900. Upper bound, 5,100. Your average value, 5,000. And your standard deviation, 50. We're going to type that in the calculator. So the second bars, option 2 for normal CDF, 4,900, comma, 5,100, comma, 5,000, comma, 50. And I get 0.954. So about 0.954, which means I have about a 95.4% chance of getting between 4,900 and 5,100 heads when I flip a coin 10,000 times. That's it for using normal PDF and normal CDF. Hopefully it made sense to you. If you got questions, let me know.